Hi there, and thank you for clicking on this video. This video lesson is going to take us through what I have called laws of exponents 2. This video is going to focus on an exponent of 0 and negative exponents, what they are, what they mean, where they come from. Please give this video a thumbs up if you find it helpful. Drop a comment if you have a question or just have thoughts about the lesson in general, and check out the practice set for this lesson. I always say that at the beginning of my videos. But it is so important that you're not just getting a lesson, but also getting a chance to practice it, especially if you are using this to supplement instruction from your regular classroom. So without further ado, let's start with what we've covered before. Now, what I am going to do is I'm going to quickly summarize what we've already covered in terms of laws of exponents. I'm going to go ahead and link the video for that lesson in the corner above. So previously, we have covered this law, which is x to the a times x to the b is equal to x to the a times b. So that would look something like this. If you had x to the third times x to the fourth, that would be equal to x to the seventh. So we know when we are supposed to add exponents. Next one is x to the a raised to the b. Sometimes this is called like the raising a power to a power, an exponent to an exponent. And in that case, we multiply exponents. So if I had x to the third power raised to the fourth power, that would be x to the 12th power. And lastly, we talked about when we would subtract exponents, and that is when you are dividing what are called like bases. And so if I had x to the fourth divided by x to the third, that would be equal to x to the first power. And what is important to note about that, it's always the exponent in the numerator minus the exponent from the denominator. And sometimes I have seen students draw the wrong conclusion about that, where they think, oh, it's always the bigger number minus the smaller number. No, it's the numerator exponent minus the denominator exponent. Now, if you were looking at that and thinking, oh, that's what I needed a lesson on, okay, I'm not sure about those laws. I actually don't need to do exponents 2. I need exponents 1. I'm going to go ahead and link the video for that up in the corner there, so you can check that out. And then once you've had a chance to see that and practice with those laws, and then come back to this video and you can resume right here where you have left off. Now, what about an exponent of 0? Okay, so when we get here, okay, our definition of an exponent meets some limitations. If you think back to when you are first told what an exponent is, it's usually defined as it shows us the number of times that something is used as a factor. So for example, 3 squared means that 3 is used as a factor. That means it's being multiplied in twice. And so you have 3 times 3, or 9. And then we expand that to like x to the fourth means that x is used as a factor 4 times. And we don't really have any issues with that. However, once we get to some like weird exponents, it really breaks down. And I know in the sequence that I'm doing for my YouTube channel, I've already covered rational exponents. So we've already seen that kind of break down, like how can something be used as a factor half a time. And if you'd like to see my lesson on that, I can't link more than one in a card, but I'll try to remember to link it in the description box so you can go and check that out. But what we need to do is we need to derive the meaning of these exponents by building on what we know. So take a moment and think about this. What does your intuition tell you that 5 to the 0 is equal to? I'll pause for a few seconds and let you think. All right, now you might have said 0, but this would be wrong. And most of the time when I toss that out to my own students, that is what I get. 5 to the 0 is equal to 0. And it's not like a crazy conclusion. if the exponent tells you how many times something is used as a factor, and then we say the exponent is 0, then it is very logical to say, well, if it's used as a factor 0 times, that means I have no factors, which means I have nothing, right? Like I'm not writing anything down. So it's not this illogical conclusion. So if your intuition told you that 5 to the 0 was equal to 0, I don't want you to think that you missed something obvious. You did not miss anything obvious. That is what most of our guts tell us. Now, maybe your gut told you something else, or maybe you've seen this before, or you thought, oh, 0 is too obvious, right? It can't be 0. I'll pick something else. But let's go see why it's not equal to 0 and why it is equal to what it is equal to, because we want it to make sense. So here's our method. What we're going to do is show the meaning of an exponent of 0 by working the same problem 2 different ways. So we're going to start with the same problem, and then we're going to kind of proceed according to what we know. We're going to land in 2 different places and then draw a conclusion from there. So the problem we're going to look at is 5 to the third divided by 5 to the third. So one way that we can do this is to use the laws of exponents, and it's important that we've already covered when to subtract exponents at this point, because that's about what we're going to invoke here. We know from our previous study of exponents that if we are dividing the same base, we can subtract exponents. So I can do this and write it as 5 to the 3 minus 3, okay? And then, of course, 3 minus 3 is 0. And that's where we're getting that 5 to the 0 from in the first place. All right, so there's where we can arrive at a 5 to the 0. So by subtracting 3 minus 3. Now, below, I'm going to take the same problem, okay, and I'm just going to reason it a different way. 5 to the third is 125. So 5 times 5 times 5 is 125. So this is 125 over 125. And I know that anything divided by itself is 1. Now, here's the reasoning. If I am confident that this top line works, which we should be, we know that we can subtract those common factors, right? Not common factors, subtract the exponents, subtract the exponents. And I'm reasonably sure that I've done this bottom one, right? Like 125 goes into 125 one time. Then my conclusion is that these 2 expressions must be equal to each other. And so that brings us to this conclusion here. Therefore, 5 to the 0 is equal to 1, not 0. Does that go against, for a lot of us, our intuition or our gut? Yeah, but it's not unreasonable. We can see the layout of the proof there. Now, if you really don't believe me, go grab a calculator, okay, and type in 5 to the 0 and see what the calculator will tell you. Now, here's the general rule. I picked a 5 there with an exponent of 3, but we could do that with any number, any variable. If you raise it to the 0 power, you do get a 1. And so that's our general rule of what exponents of 0 are, what they mean. So you see an exponent of 0, then that is equal to 1. And I'm looking at the practice set, and I don't think I put a whole lot of that in the practice set, but there's a reason for that too, and that kind of has to do with how I do these problems. Now, negative exponents can be reasoned in the same way. So we're going to take this problem here, x squared over x to the 6th, and we're going to work that problem out 2 different ways and show that they must be equal. Now, I picked for this purposes a 2 and a 6, but you could pick any numbers that you wanted there, just as long as the numerator exponent is smaller than the denominator exponent. So this one's going to give us an exponent of -4, but if you could do this for -5, -3, like so without further ado, what do we get here? Now, we know from, again, our previous study of exponents that when we divide like like bases, we subtract the exponents. So this would be 2 minus 6. Again, always the numerator exponent minus the denominator exponent. And 2 minus 6 is negative 4. So that's where we get the negative exponent from. We get it from using that law. Now, on the bottom here, I'm going to take that same problem and I'm just going to pull it apart a different way. In my denominator, I'm going to expand it and say, okay, that is x times x. And in my, I think I said denominator, that is the numerator. In my denominator, I am going to expand out the x to the 6. Now, what I'm going to do in the numerator here, which might seem a little weird, but I am going to put a times 1, and hopefully we can agree that, like, sure, this seems a little weird, but like multiplying it by 1 doesn't change it, so sure, go ahead and do times 1, times 1, times 1, whatever. Now, what we studied before in the previous lesson is that each of these, like x divided by x, that's equal to a 1. That's why they cancel out. Then we have those canceling out. And what I am left with now is the 1 in the numerator. So the reason I wanted to put the 1 there was because if I don't put it there, I get a lot of students that say, oh, nothing, like nothing is left in the numerator. Well, it's not nothing, it's a 1. A 1 is what we're left with there. So we want to avoid the pitfall of saying, oh, that's got to be a 0. No. Now, in my denominator, I have 4 of the x's there. And so x times x times x times x is x to the 4th. Okay. And same as with the exponent of 0, if I am reasonably sure that both of these lines have been executed correctly, then they must be equal to each other. X to the negative 4th must be the same thing as 1 over x to the 4th without the negative. And so we'll go ahead and write that over here. Therefore, x to the negative 4th is equal to 1 over x to the 4th. And again, I picked a 2 and a 6, so we landed at x to the negative 4th, but we could do this and just pick different numbers to get x to the negative 1, x to the negative 2, 3, 4, 5, like whatever. Whatever you wanted to pick, you could pick those numbers that would come out to that, and you would execute the same reasoning, and you would land at the same place. So the general rule here is that x to the negative a is equal to 1 over x to the positive a. Now, a lot of times you'll see in the directions, write this with a positive exponent. And every year I will get kids that just like erase the negative sign. I'm like, no. The way you go from a negative exponent to a positive exponent is, in this case, putting it in the denominator. You take that factor, put it in the denominator, and the exponent would then be positive. Now, I do want to note this: a negative exponent is not a negative number. So I will get this a lot. Okay, if somebody says 5 to the negative 2, I will get students say, oh, well, that's negative 25. No, 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 no. Okay, no, because that negative exponent is not indicating a negative number. And so I get that a lot. So what is it equal to? Well, if we follow that law of exponents, that would be 1 over 5 squared. Okay, so we take that negative exponent, we kick it down into the denominator, and so it would be 1 over positive 25, not negative 25, okay, not the same thing. So that negative exponent does not indicate that you have a negative number there. Very, very easy thing to kind of trip up on. All right, so last thing we really want to talk about is, what if the negative exponent is in the denominator already? So you've got 1 over, and then the thing that has like the exponent in it is like the exponent's already negative, but it's sitting in the denominator. So this is something that I always take my students through. I've never asked them to duplicate the process, but I don't ever want to just give people like, here's a rule, follow it. We want to see that the rule makes sense. So the first thing I'm going to do here is I'm going to copy over the 1 over, and then in my denominator, I'm going to kick in what we just covered. All right, so x to the negative a is 1 over x to the a. Now, this right here is what we call a compound or a complex fraction. It is a mess. It kind of looks scary. I tell my students, compound fractions look scary, but they're actually not. They're really not bad to listen to deal with. What we are going to do to work our way through it is we're going to remember this factoid, that a fraction bar is really just a division symbol. So I could replace that fraction bar with a division symbol, and you could actually do it twice here. I'm not claiming this is the only way to do it. But instead of saying 1 over x to the a, I'm going to rephrase it as this: 1 divided by 1 over x to the a. And what I did there was I just removed one of those fraction bars and went with what I know is an alternate notation. Now, right here, we're going to invoke the definition of division, which if you go way back in my video series, way back to like it's somewhere near the beginning of Algebra 1, if you go to my Algebra 1 playlist, and we get into like what are the operations, and I define division as multiplication by the reciprocal. So this would be 1, and now instead of the division symbol, I'm going to have the times sign, and then we're going to take the reciprocal of 1 over x to the a, which would be x to the a over 1. Some of you might be familiar with that from, say, a middle school level as keep, change, flip, which I hate because it's a little rule and then like nobody knows why it works. So somewhere on the channel, if you want to go digging for them, I have some videos. If I can go find them and link them in the description box, I will, which means I should probably be making a note of all the things that I said I would link in the description box, which like I've kind of already forgotten what they were, but think on it when I'm processing the video. But anyway, so we want to know like why that works. But anyway, so we've got 1 times something divided by 1. Well, something divided by 1 is just the something. So I'm going to go overkill with this really bad here. Just bear with me. This would be x to the a, and then 1 times x to the a is just x to the a. So what do we get with that? We end up here. Therefore, 1 over x to the negative a is a way of writing x to the a. Okay, I'm trying to decide if I need to pause the recording. Maybe. But I haven't done it yet. So 1 over x to the negative a is just like a messy way of saying x to the a, so that it's back up in the numerator. If you go back here, we've got the x to the a, it's like in the numerator. So what does that mean? Summary of our negative exponents. Having a negative exponent means to take the reciprocal of whatever has it. It essentially means it changes, it being the factor that has the negative exponent, it changes position from numerator to denominator and vice versa. So here's what it means. If you have, say, y to the negative 3 over x to the negative 2, this y to the negative 3 right here, okay, because it's got a negative exponent, that would go to the denominator and become y to the 3rd. And this is what we just did. If you got a negative exponent that's in the denominator, that's going to kick into the numerator and the exponent is going to become positive. So essentially, that negative exponent means to take the reciprocal. And again, I'm looking at my practice set here, and it's a good practice set, and it covers a lot of stuff that I was trying to be very intentional about okay, we want to look at all these things. And as I'm looking at it, I'm realizing, okay, well, there's still stuff that I missed. So if you saw something like this, like x over y to the -1, that -1 is essentially telling you, hey, take that reciprocal of the entire thing. So that's really what negative exponents are, what they do. And now you've seen the breakdown of it. Once you see the breakdown of it, then it's really an issue of becoming fluent in using it. So let's take a look at an example problem here. What I love about these kinds of problems is that there are always multiple ways of doing these problems. So what I do here is not necessarily what you would have to do, and we'll see how we are on time, whether I can do this more than one way. So now, these all assume that we know the previous rules of exponents and we have worked through those. So first thing I notice about this is I've got an exponent outside of the parentheses, and that I can rewrite that by multiplying that through. So we would have 2, and it would be 1 times -2, so that's 2 to the -2. And then x to the 4 times -2 gives me -8. And I'm not going to do too much at once with that because the more you, well, as with anything in math, the more steps that you're trying to hold in your head and say, well, I don't like to write stuff down, the greater your chances are that you lose track of stuff. Now, we've got to deal with these negative exponents. Anything that has a negative exponent attached to it is going to change position. So the 2 right here is going to come down to the denominator, and it's going to become 2 squared instead of 2 to the -2. The 8 is going to come down to the denominator and become x to the 8th, not -8. And the 4 here is going to move up to the numerator and become 4 to the 3rd. This right here, this x squared, that has a positive exponent, so that is going to stay put. So we're going to have 4 to the 3rd in the numerator, 2 squared, and then x to the 8th come to the denominator, and the x squared was already there. Now we've got some stuff to do with like the constants, like we got to simplify it further. So 4 to the 3rd power is 64. 2 squared is 4. Like when that happens, it's because I was looking ahead at this and I saw the number 8, and so that's what comes out of my mouth. And then we have x to the 8th times x squared, which is going to give us x to the 10th. And then last but not least, I can do that 64 divided by 4, and that is equal to 16. And so this reaches 16x over x to the 10th, and that would be my final version. Now you might look at that and say, well, what if I didn't do it that way? What if I did this? So instead of that first step that I took where I multiplied the exponent through, what if I just take that whole thing with the exponent -2, move it down to the denominator, and we'll move the 4 to the -3rd up. And so we'd end up with 4 to the 3rd over, and now like that entire thing comes down and it becomes an exponent of +2. Now, a lot of students wouldn't want to do this, because now they would look at that x to the 4th and say, wait a minute, if I move the x to the 4th to the denominator, shouldn't that have become a negative exponent? No, and the reason is because that x to the 4th is protected in the parentheses. It's this exponent that is doing the lifting of moving it to the denominator. 4 to the 3rd is still 64, and now here you would have 2 squared x to the 8th. And I hope you notice that once we get there, it is the same expression that we had doing it the other way. So there are options for how you want to do this. What I tell my students is one of the ways that I will catch students cheating is if they start the problem one way and then kick over to another, like a different way of doing it. Now, both ways could be right, but they don't meet in the middle necessarily. So an example would be this: if you started by writing this and then jumped over to this step right here, so it's almost like you multiplied the exponent through and then unmultiplied it, and like nobody does that. That would not be that would be backing up a step instead of moving forward. And that's usually how I can kind of catch that a student has maybe started, got stuck, and then they copied off a neighbor without evaluating whether or not their neighbor was doing the problem the same way with the same series of steps. Now, what it means to simplify these expressions can be nuanced. That means that there's some subtleties to it and maybe some flexibility. It often means to write the expressions with no negative exponents. So your final way of writing it will have no negative exponents in it, and where each factor only appears once. And what we mean by that is, like, see how the x is here twice. We don't want to have like x to the 8th over or times x squared. We want to merge that so that there's only one x. So you don't have x's on the top and bottom. You just have like one x, one y, 1, 2, like one number, one of each thing, with all positive exponents. However, always follow your teacher's directions for how they want the final answer to be written. If you are reviewing this, say you're in a calculus class and you are stumbled across this video to review this, you know that in calculus, we would rather have negative exponents than we want rather than fractions. And so you would probably use negative exponents as a way to not write fractions. So that's an option. So always follow what your teacher says, like they want, for what it means to simplify. Please don't forget to give this video a like if you found it helpful. Drop a comment or a question. I am going to star this again. Obviously, I did that when I put this together. Check out the practice set for this skill. The practice set, which I will link below, is just filled with like a lot of review. These concepts are usually fairly simple until you throw them into a messier problem, and then you've really got to think. So please check that out and subscribe to the channel for more math content. Super easy, just a little button to click. And I hope that I will see you in a future video.